electromagnetic induction, and then I prepared a bunch of experiments which illustrate this process. All right, so now we finished actually with a process which is called induction. And let me remind you that it is a process that if we have two solenoids which share magnetic flux, then if we force current to flow in one solenoid, then the other solenoid immediately will induce electromotive force. This process is called induction. At this point, actually, I recall that I should make a digression because somebody asked me about it. What are relationships between various words, like a coil, solenoid, electromagnet, and inductor? Well, we didn't talk about how inductor works yet, but that's okay. Yeah, because in order to make a solenoid, we have to wind wire. We have to make a coil of wire. So you could, in principle, say that every solenoid is a coil. However, not every coil is a solenoid. We can coil, for example, a garden hose, and then we will have a coil of garden hose, but this is not going to be a solenoid. Solenoid is a coil made of wire, and the purpose of it is to run current through it. Now, it could be done for various purposes. We can use solenoid to make magnetic field, and if we use it to make magnetic field, then this solenoid is going to be called an electromagnet. When current flows through the solenoid, we have it produces magnetic field. Current doesn't flow, magnetic field disappears. And actually, those electromagnets can produce quite strong magnetic fields. Another application of a solenoid is to make, for example, parts in electronic equipment. So one of those devices which we discussed was a transformer. We take two solenoids, assemble them in such a way that they share magnetic flux, and then we have transformer. Now, the device which we discussed in the past, an inductor, is also a solenoid. It's a relatively tiny solenoid. Well, so I mean, in electronic instrumentation, transformers are also relatively small. And the purpose of this solenoid is to relate current flowing through that element with the potential difference across this element in a particular way, that the potential difference is proportional to the rate of change in the in current. All right, let's now take a look how an inductor works. An inductor works because it's because of induction, which is a process, and most specifically, it's because of a process called self-induction. Now, self-induction is very similar to induction, except that the current flowing in a coil actually produces electromotive force in the coil itself. It's the appearance of that coil in the electromotive force in the same coil in which the current varies is called self-induction. So let's imagine how it works here. So let's say that we have a coil and we connect it to a source of alternating current. Electromotive force, which is induced in that coil, is going to be opposite to the rate at which magnetic flux is varying. I'm using here Faraday's law of induction. And if we have n loops, then electromotive force will be n times times the rate of change in the magnetic flux through a cross-sectional surface of a solenoid. So you have to imagine that we cut this solenoid horizontally. All right. Now, let's recall how, well, what is the flux? Flux will be scalar product or integral of a scalar product of surface vector and magnetic field. And well, since in a solenoid magnetic field is uniform, and if we take cross-sectional surface which is horizontal, so normal to the surface and magnetic field vector are in the same direction. So when we calculate scalar product, we will have magnitude of the first vector times magnitude of the second vector times cosine of 0 degrees. Now the first vector, magnitude of the first vector is the area, cross-sectional area of that solenoid. Magnitude of the second vector is magnetic field strength. And in a solenoid, magnetic field strength depends on number of loops per unit length of the solenoid and the current flowing in the solenoid. We have just to multiply it by permeability of free space. So this expression gives me a function which describes magnetic flux when the current in the solenoid is I. Look, notice that all the remaining symbols represent constants. They are independent of time in the same, right? So I can take out all the constant in front and relate electromotive force produced in the solenoid with the rate of change in current. Does it give you idea to do something? What is it? Well, I mean, we have already, I mean, this gives us a way to make a certain device for which electromotive force, now recognize that electromotive force is electromotive force induced in that coil. Well, if internal resistance of the coil is small, then it's really potential difference between this point and this point. Yes, Adam, say it louder.
Well, then that would just be potential difference is proportional to the rate of change.
Yeah, potential difference is proportional to the rate of change in current flowing through that element. What device has this property? An inductor, right? So this is how to make an inductor, and actually we already see what will be the inductance of the inductor. Now there is some there could be some kind of a confusion about plus or minus. Yeah, because well, it's this electromotive force is opposite to the electromotive force really produced by this source. So the potential difference which we took when we discussed inductors were flipped. I mean, we flipped the terminals to make them more consistent with the other elements. Now, in an ideal inductor, will be made from a wire whose, from a material whose resistivity is 0. So the only way actually to produce potential difference between the terminals of that inductor is because of self-induction. Self-induction is the source of potential difference across this element. And in practical cases, it is that if frequency of the current which we run through that coil is high, then indeed resistance makes a small contribution to the impedance of this element. A real inductor behaves like an ideal inductor connected with a resistor in series. All right. So the electromotive force induced in the coil is proportional to the rate of change in the current in the coil. And inductance of a solenoid depends now on the area, cross-sectional area of the solenoid. Permeability of free space is a constant, square of number of loops, and inversely proportional to the length of the solenoid. Now what would happen if instead of having an empty solenoid, we put a core, a ferromagnetic core, where the calculation would change? Let's see. Will this step be the same? We say? It will have the same flux. It is flux through the cross-section of the cross-sectional surface of the solenoid. All right, so the first step will be identical. Let's see for the second step. Would the second step be identical? Adam says no, and Adam is right. We would have to incorporate here what? Yeah, because indeed, magnetic field produced inside of the core is now greater than when we had an empty solenoid. By what factor? It would be good to remember 1 plus susceptibility of the core. So the inductance, after all, inductance will have a term of a factor which involves susceptibility of the core. And actually cores in the solenoids, I mean, take a look one day into your TV set and look for the elements which we discussed. And you will find out also those tiny inductors. And you could see that in tiny inductors you could screw in or unscrew the core. I mean, this ferromagnetic, you can move this ferromagnetic part deeper or shallower. And depending on this, how deep you put it in, you can adjust inductance of this inductor. Well, because why would you do that? In what circuit, for example, it would be important that to adjust inductance to appropriate value? I mean, it would be very important to adjust it to appropriate value. In a resonant circuit, you have to tune that radio or TV to appropriate stations. So the combination of capacitance of the capacitor and inductance of the inductor determines what frequency you are going to receive. All right. Well, similarly, like when we discuss electric field, and we recognize that energy is associated with electric field, magnetic field also contains certain energy. So what we will do now, we will think how much energy we can drain from a field when we destroy it. All right, so what I will do is now I imagine that we are destroying magnetic field and figure out how much energy is obtained. So in other words, we will have to calculate how much electrical energy is delivered, or actually minus energy which is delivered to that solenoid in time from the initial magnetic field to the magnetic field when it is completely gone. All right. Now, electrical energy is associated with the current flowing through the element and the potential difference across the element. So I mark it current at certain time between 0 and t, and inductance multiplied by the rate of change in current gives me the potential difference across the solenoid. Now I can recognize that here I can change easily variable. Rather than having time as the variable, I can change it to current. I would have appropriately to change the limits as well. So from the situation where we have 0 current to the current which produces this magnetic field. Well, if we integrate that, I will have that this is 1/2 of inductance of this inductor multiplied by square of the electric field. So this is amount of energy which is stored in an inductor when we have current flowing through this inductor. Well, I would like to relate it, to express it rather than in terms of current. I would like to relate it to the magnetic field strength. And also I'm more interested in the energy density rather than density in entire coil. So what I have to do is I have to divide this energy by the volume. And this is from the definition of energy density. Now, since magnetic field inside is uniform, rather than having differential relationship, I can just divide total energy associated with the magnetic field in the coil divided by the volume of that magnetic field. A magnetic field is approximately only inside of that solenoid. So I took now this expression and plug it in here, and now I want to relate it to magnetic field. So actually I reversed now the relationship between magnetic field in the coil with the current in the coil and substituted. Because when we discussed magnetic field produced by the solenoid, we related magnetic field to the current flowing in the coil. So from that expression I calculated how current is related to magnetic field, and I put it in here. Yes, I can recognize that I have, well, number of loops per unit length of the solenoid, permeability of free space, and magnetic field. So this expression actually represents current, relationship between current, or I express current in terms of magnetic field strength. And this expression is the expression for inductance of the inductor. And it looks quite complicated, but a lot of those things cancel out. You can recognize it. You have area here and area here. You have length of the solenoid, length of the solenoid, and length of the solenoid. Number of loops squared, number of loops squared. So after simplification, we will find out that magnetic field density or energy density is just proportional to the magnetic field strength. Recall that for electric field, we also had a relationship that energy density associated with the electric field was proportional to the electric field strength. Now, in case of electric field, the coefficient was 1/2 times permittivity of free space. In case of magnetic field, we have 1/2 times permeability of free space. All right. So this will be. I'll make a break over here, and show you several things in which you will see evidence of magnetic induction. I'll start with this experiment. I have a coil over here, and this coil is connected actually to a regular socket, so I can run alternating current through this coil directly from the socket. And well, how about if I take it this way? Oh, and inside there is a iron core. Iron is a ferromagnet. Let me turn this thing off for a moment. So it enhances magnetic field strength. So I can have pretty substantial magnetic flux coming out here. Well, and here I have a loop, well, several loops of wire connected to a light bulb. So, oh. So, now when you see that it glows despite actually I didn't connect it to anything. How about if I get rid of this? So you saw here an example of, what was that? It's a model of something. Of a transformer, correct. Now I can show you something more exciting. I put a ring on this, and when I turn the current on, oops, it jumps. Would you like to do it too, Owen? Yeah, so you just push it? Yeah, I'm watching myself. I'm watching myself. Try again.
I didn't work this time.
Huh?
At your face.
Yeah, what did I do?
Did you disconnect them?
I'm pulling his leg. Yeah, why? Why it didn't work? I'm going to try. Well, who noticed what I did? What say? No. I have two rings. Now, why actually this ring jumps? Let's start with this, why this ring jumps. Well, because the variable magnetic flux flowing through, through this core, I hate say flowing, we shouldn't say flowing, it just is, produces electromotive force in this ring. Well, and if it produces electromotive force, according to Lenz's rule, well, current, it will try to make current flowing in this ring. Well, when the current flows in this ring, it becomes like an electromagnet. And actually, according to Lenz's law, the two fields, field produced by this coil and by this coil, are going to be in opposite direction. So it will be something like bringing magnets with the same type of a pole toward each other. So they will repel. Well, what I did with Owen, I gave him a ring which cannot produce magnetic fields. It's also aluminum, though. How? What should I do in order to prevent magnetic field to be produced by this ring? Well, since I played it on you, why don't you find it out? It's cut, right? So electromotive force is produced in this ring, but it's not a full ring. It is cut over here, so current cannot flow. And if current doesn't flow, then electromotive force is not produced at all. All right, now I think and here we have a model of a power station. In a power station we use something to turn generators, and when generators turns, it produces electromotive force. Now obviously in real power stations we don't use electricity to run the engines, because here I use electricity to boil water to run this steam engine, and that steam engine runs the generator. Okay, so let's stop this. Oh no, one thing. I want you to see something. Listen to the engine. Have you noticed something interesting? You probably noticed that when the light bulb was in the socket, the engine worked harder. It couldn't turn it as fast as without the light bulb. Now, why it would do that? Actually, it's also a result of current flowing in that loop. It is that when just electromotive force is produced in the loop, in the rotor, in the rotating loop, and current doesn't flow, it doesn't produce magnetic moment. I mean, that rotor doesn't have magnetic moment, so actually the torque required to rotate the rotor is relatively small. The magnetic, I mean the torque, because what the engine does, it fights with that magnetic torque, which the rotor, actually the magnet exerts on the rotor. Yeah, because the rotor is in magnetic field of a magnet. Actually, how about if we see how it works? We'll think just about one loop. Oh, actually, we can think about many loops as well. Now, let's say that we have magnetic field in this direction, and rotor rotates that way. So now I consider normal. I mean, this is a how about, I'll put it A. This is a surface vector, so magnitude of it is equal to the area of the loop of the rotor, and the direction is perpendicular to the surface. Now this is magnetic field. It's an electromotive force induced in this loop. It's going to be equal to number of loops times the rate at which flux is varying with respect to time. Magnetic flux. All right, now let's say that rotor rotates with, so the magnitude of angular velocity is omega. So in general magnetic flux we will have to differentiate now product of this product. So I can write it down explicitly. I mean this scalar product, I can write down that this is area of the loop times magnetic field strength times cosine of the angle between the two vectors. Let's say that this is that angle, and this angle varies with time. I can write down, if it rotates at a constant angular velocity, so this angle at instant t, if I choose reference for time appropriately, I can just write that that angle is proportional to t. Right, at instant t equals 0, angle is 0. Right, so I can write down that way. Actually, it will be even nicer if I put minus over here like we have it in the Faraday's law of induction. Let's now calculate this derivative. Area of the loop is time independent. I can take it in front of the derivative. Magnetic field strength produced by the magnets in which that rotor rotates is also time independent. I can take it in front. So I will have minus number of loops, area of the rotor, magnetic field strength, and now we have to calculate the derivative of cosine omega t. It's a composite function, right? External function is cosine function, internal function is omega t. It's a linear function. So if we use chain rule, derivative of cosine is minus sine, so I will get rid of this minus, and we'll get here sine of omega t. And the derivative of internal function is omega. And actually this derivation is very important for our technology. Does this resemble something? Now if I rotate it, if I rotate that rotor with angular frequency 2 pi times 60 hertz, and I adjust those quantities in such a way that with this value of angular frequency I will get here 170 volts. What do I have? A what? Yes, we will have an alternating current which we have in the wall. I mean, so this is the, I mean, it isn't, I don't think that the generator will in the power station will produce it that way, but if you go to a hardware store and buy one of those portable generators, this is how they have to work. Those portable generators right away will produce a type of a current which we have in our sockets. All right. Oh, I wanted now to show another example of induction of currents. They can be induced even in a piece of metal, flat metal like this. This type of currents are referred to as eddy currents. And so if I and now I'll make it swing. Oops, I didn't mean that. Yeah, the eddy current, the current which is induced in this piece of metal causes that this piece of metal stops. Now, I'll make over here we have an obstacle for that current. That current cannot flow so easily because of those slits. Look how this thing is going to swing. Did you see that it is not stopped as fast as the other one? And now let's go even further. Cut it that way. Oops. Eddy current cannot flow in this, and therefore it swings more. Oh, actually I should not turn off the lights. And at the end now I would like to play a little bit with a transformer. I'll make a transformer. Let's remove this. All right. So I will put two coils. Now how about if I put two identical coils? Both of them have 400 loops. And I put them on a common core and close it even here. So that core actually prevents the flux from escaping. So the fluxes are almost equal. And so I will measure potential difference which is created on one side and compare it with the potential difference on the other side. All right, so we have one thing, and now one more. let's now change frequency to, I mean, comparable to the frequency which we have. Oops. So to let's make it 60 Hertz. And how about if we now output voltage is the output from the power supply. So this is really the input on the transformer. And let's have at the same time output from the transformer. Okay, let's stop it. I'll try to have a higher frequency. Well, what do you see here? So the input, the input is 5 volts. Yep. Potential, I mean, peak value of the potential difference connected to this coil is 5 volts. Theoretically, I mean, if if these are identical coils, and if they share exactly, I mean, complete flux, what should be relationship between the voltages? They should be equal, because in both cases, both are proportional to the rate at which flux is varying. And actually, look what will happen if I reduce sharing that flux. Yeah, because now the flux in the second coil is definitely smaller than the flux in the first coil. If I connect it, then I have a much better, although not ideal. Ideally, they should be equal. If their flux was shared completely, there would be equal. But because some of the flux produced by the first coil kind of escapes or misses the second coil, then the potential difference produced by the second coil is less. However, now let's see over here. Right now we have potential difference in the second coil 4 volts. What will happen if I put a coil which has 200 loops instead for the second coil? So the second coil now will have fewer loops. I will be doing it, and you can talk to each other what you expect and why. So potential peak value of that potential difference dropped by a factor of 2. Why is it so? Because electromotive force produced in a coil is proportional to the number of loops. So if we reduce number of loops by a factor of 2, the electromotive force dropped by a factor of 2 as well. I have one more coil which contains 800 loops. You may talk to each other what will happen and try to do it faster than you see it. What's the peak value of voltage now? 8. Let's see. So we have to change. And it is indeed 8. All right. So this is all for today. Have fun tomorrow.